Hi, in this lecture, we will talk about boundary conditions and some best practices in CFD simulations. So for inlet boundary conditions, the most common choice is an inflow boundary condition where we prescribe a velocity profile at the inlet. For example, a uniform velocity profile or a parabolic velocity profile. And if we know the flow rate coming into the domain, we can still impose velocity by simply dividing the flow rate by the cross-sectional area. And of course, mapping that to the appropriate velocity profile, such as the parabolic velocity profile. We can also impose pressure at the inlet if that is the value that we know instead of velocities. We also have that choice. Now, there are some notes that in the inlet boundary condition, you can think of it as a source for fluid flow. It's really what's driving the flow. And therefore, you also need some outlets or sinks that can absorb the flow that comes into the domain so you can conserve mass. So whatever flow rate enters has to exit your domains. And your inlet boundary condition should also always be far away from the region of interest unless you exactly know the velocity profile at the exact location. For example, let's say you have incoming flow into some domain and you have some complex geometry or some physics happening here that leads to complicated flow patterns. You never want to impose your inlet boundary condition right at this edge where is your region of interest. So this might be actually your region of interest. You only care about this region, but you'll never set the boundary condition at the inlet right at the edge of that region of interest where you care about. You make sure you set it a little bit upstream. If you know the exact velocity profile at every location, you can go slightly upstream and there set your inlet boundary condition. But if not, you have to make sure you're sufficiently downstream, or rather sufficiently upstream to the region of interest where you're defining your inlet boundary condition. For outlet boundary condition, zero pressure is a very common outlet boundary condition that's used in combination with an inlet velocity boundary condition. In the finite element formulation using the stress based weak form, zero traction is the equivalent or common choice. And what that really means, if you have a zero traction boundary condition or zero Newland at an outlet, it means that your pressure at the outlet is balancing the normal viscous stress, okay? And you can also think of some of this in the context of a fully developed velocity profile. So when at an outlet, if we have, let's say, zero normal viscous stress, then that means that you have a fully developed velocity profile or partial length equals zero. For incompressible flows, if inlet boundary condition is in terms of velocity, then the absolute value of pressure that you set at the outlet does not affect the flow. It just scales your pressure values. And in an incompressible flow, the absolute value in most cases don't matter. The only case that the absolute pressure value matters in an incompressible flow is if you're doing there are two cases. If either your boundary condition at the inlet is in terms of pressure, then of course that matters what you set at the outlet pressure. Or the other case that also matters is that when you're doing fluid structure interaction simulation. So if you're doing FSI simulation, the absolute value of pressure will also matter because that's going to be the force that's going to determine the force transmitted to your solid and your structural deformation. So if you're doing rigid wall, then the absolute value of pressure at the outlet doesn't really matter. It's just going to scale things. And of course, if you have multiple outlets, then still the absolute value of pressure doesn't matter. It's really the relative value of the pressure differences or the ratios between the outlets that's going to determine the flow split ratio. That's going to be important. So similar to the inlet boundary condition, that should be far away from the region of interest where complex phenomena happen. The outlet boundary condition should also be far away downstream of the region of interest. So for example, if you have some recirculation, complex flow happening here, you'll never want your outlet boundary condition to be right in that region. You also don't want your outlet boundary condition to be right after that. You want to make sure it's sufficiently downstream of that region where complex stuff are happening, like recirculation. You also can impose prescribed velocity as outer boundary condition, but that's usually not a good idea and not recommended. If you're doing prescribed pressure on your outlet, that's usually done as a constant, spatially constant pressure. And finally, a common thing that happens in a lot of CFD simulations is that you get artificial backflow at the outlets. So, and these backflows are not physical. You get artificial backflow at the outlet, and that they can cause divergence problems. To resolve the issue, the easiest way, one way is that to just extend your outlet sufficiently, make sure it's sufficiently extended. The second choice, which is a better choice and more efficient, is to use backflow stabilization methods. There are different backflow stabilization methods developed for finite element simulations. I'm including a paper here. I'll include a link in the description box where you can see these methods that are used for backflow stabilization. Some of these methods, directly change your weak form. Basically, the integral term that you have for your Newman boundary condition, they add a stabilization to that Newman integral boundary term on the face of the outlet, on the part of that boundary integral term that corresponds to the outlet. You can add some sort of stabilization there to improve or get rid of backflow stabilization. So you can check out this paper for details about that. Okay, so for the walls, if you have rigid walls, we use no slip, which means zero tangential velocity and no penetration, zero normal velocity, or just zero velocity vector. If our wall is porous, we still use no slip or zero tangential velocity, but for normal velocity, we no longer necessarily impose zero normal velocity for a porous wall. If you have a moving mesh problem, the mesh velocity is prescribed at the wall. And if you're dealing with nanoflows, you have to be careful that the no-slip boundary condition does not hold anymore, and you need to have special kinds of treatment there. So for Dirichlet boundary conditions, so if we are dealing with so to impose the Dirichlet boundary conditions, so far we mentioned that when we defined a space of functions, trial functions, we define them such that on the boundary they are equal to a Dirichlet boundary condition. In other words, we're enforcing the Dirichlet boundary condition in a hard, exact way. And we didn't mention how we do that, but here with a simple example, I'm going to show you. So the way we do that is that at the end of our finite element formulation, when we arrive at this linear system of equations that we solve for our unknown, for example, U in this case, if one of these values are Dirichlet values or Dirichlet nodes, what we do is that we modify this matrix on the right-hand side such that we guarantee that that Dirichlet boundary condition is enforced. So, for example, if in this simple example, I know the value of U1, so the node 1 is on a Dirichlet boundary, which I know what the value it is, so if that's equal to UBC, what I do is that simply I zero out that row that's getting multiplied by U1. So in this case, this is the row that sorry, I zero out the row that corresponds to the U1. So in this case, the first row. And basically, I just put all the entries that are going to get multiplied by U2 and U3. I set them to 0. So if you look at these two zeros here, when this gets multiplied by this column, U2 and U3 will be 0, and U1 will be multiplied by 1. So for the first equation, I'm just going to get U1 on the left-hand side, and on the right-hand side, I replace this B1 by UBC. So therefore, here also, what I'm going to see is that the first equation that I'm going to get when I multiply this by the column equal to the first row, which is UBC, I'm going to get U1 equals UBC. So I am essentially overwriting my linear systems of equations that I derived such that my Dirichlet boundary conditions are guaranteed to be satisfied. So that's how we impose the Dirichlet boundary condition. So finally, the symmetry boundary conditions. If you have symmetry boundaries, you set the normal velocity to be 0 on those boundaries, and any other variables, you can set the normal gradient to be 0 on those boundaries. So pretty quick, some basic best practices for CFD simulations. So first, sources of error, we can have discretization errors, and these errors are, we can refine them. We can improve discretization error by choosing a smaller mesh or a smaller time step. And also these errors depend on the order of accuracy. For example, are we using a first order time integrator or a second order time integrator? Then we also have iteration and convergence errors. A lot of the algorithms that we deal with, for example, nonlinear iterations, they're iterative. So then they have to stop at some point. So there's some errors there. There's always round-off errors. There's also uncertainty. So for example, the geometries that we create, the choice of boundary conditions, maybe the fluid properties, such as the viscosity, or even the choice of the rheology, the constitutive equation that we choose. All these things could have uncertainty. So the best way to deal with that is to perform sensitivity analysis and uncertainty quantification. And finally, the code errors. There could be mathematical errors in implementation. That the best way to deal with that is to do verification, meaning that first we solve the codes that we develop with a simple benchmark problem where we know the exact solution of the analytical solution. And also to deal with our uncertainties and limitations, we will need to do validation with experimental data. So then verification. So this, really, this whole topic of validation and verification is something that we should always think about when we do CFD simulation. And then in terms of our mesh accuracy, we need to make sure our mesh has acceptable quality. So we can always check the quality of our elements. So either the mesher that we're using outputs mesh quality metrics, or in some software like Paraview, we can also use appropriate filters to calculate some metrics that measure the quality of the elements that we have. We need to make sure we always use boundary layer meshing next to a no-slip wall, unless we're dealing with Stokes and low Reynolds number flows. We need to do local mesh refinement in regions that we require high accuracy and we anticipate high solution gradients. If you don't know which regions are the more complicated regions that have high gradients and complexity, we can use adaptive meshing. And the way this works is that we first solve our CFD problem, we get the solution, we calculate some metric that tells us where we're having likely more errors. And usually the easiest way is to just calculate the gradient of the solution. The regions where we have higher gradient are likely the regions that could benefit from a higher mesh resolution. So then we do remeshing based on the gradient of the solution, and then we redo the CFD simulation. So this is called adaptive meshing, and it's different from local mesh refinement. Local mesh refinement is when we do that a priori. So at the beginning, we just refine some place. We do higher mesh resolution at a certain location, and we just run our CFD simulation. So that's called local mesh refinement. For example, at the boundaries, we always know that we need more resolution at the no-slip wall for bound layers. But in adaptive meshing, we don't know that. We run our CFD simulation, we calculate the gradients, and in regions of high gradient, we, using some metrics, we refine the mesh, and then we redo our simulation. And we also finally need to make sure that we avoid sudden jumps in mesh size. So mesh elements, as we go from fine to coarse within a domain, we need to make sure that the mesh edge sizes are smoothly transitioned. And finally, we need to assess our solution. We need to perform mesh independence study and also make sure our time step is fine enough. We should check the units to make sure they're all consistent, monitor the residuals and convergence, and also make sure we do verification and validation. And also if there are sources of uncertainty, sensitivity analysis and uncertainty quantification is really helpful.